The first type of normal stimulus and response I want to talk about in relation to DHCP is the initialization process. I want you to think of this scenario. You've just bought a new workstation and you want to plug it into your network and start setting it up, downloading software, communicating on the network, all those great things, whether it's at home or whether it's work. Well, in order to do that, your device is going to need an IP address. It's going to need to be able to communicate out to the internet on the network and so on. So you plug that in, and then what happens? Well, this is what happens. It's the DHCP initialization process. So we have this interplay that's going to happen between your workstation and a server responsible for providing the addressing information you need. Now, in this case, we have a DHCP client, a DHCP server. The DHCP client is your workstation, whether it's a laptop, your phone, what have you, and whether you're plugging into the network physically or you've connected via the wireless network. You're going to have a piece of software on your machine that will provide DHCP client services. Generally speaking, that's built into the operating system. It's not something you're downloading separately. So it's going to initiate this process of initialization, and then out there on your network, you have a DHCP server. Now, on your home network, this is probably your router or wireless access point. At work, especially at a sizable organization, this is either going to be a dedicated server, or maybe it's a service running on another server, like your domain controller or a DNS server or something like that. But those are the two things we have at play here. Now, this is going to be a 4-step process, and each step along the way will use a different DHCP message type from the chart that we just looked at. Right off the bat, the DHCP client is going to send a packet to the DHCP server, and this is going to be a discover message. Now, you may be asking yourself, how is the client talking to the server at all if it doesn't have an IP address? Well, that's a good point. It's not really talking directly to the server. This is actually a broadcast packet, just like we talked about earlier. Like ARP uses broadcast to find things when it doesn't know where they are. The DHCP client in this case will send a broadcast packet out to the entire network segment with a destination address of broadcast, so 255, 255, 255, 255, and a source address of all zeros, 0.0.0.0. It can do this because we have MAC-based communication, data link-based communication to fall back on, but it's going to send this broadcast out, and the idea is that the DHCP server is the only one who's going to respond to it. So in this case, the DHCP server is going to do just that, and it's going to respond with a DHCP offer message type, and it's going to send this directly back to the client from the DHCP server, and it's going to provide an offer saying essentially, hey, I'm a DHCP server and I can provide you with the following addressing information, and it's going to provide some of that information. Now, you might think that the communication is done there, but it's not. This is just an offer. If you have an offer, you need to accept that offer. So the next thing that's going to happen is the DHCP client is going to send a packet directly to the DHCP server. It's a formalized request, and it's basically requesting to formally accept what the DHCP server is sent over, the different addressing details, so IP address, default gateway, subnet mask, all those things, whatever is configured to be sent. And the server will acknowledge that request. And at that point, the process is complete, and the system that the client in this case now has the IP address in, it can apply it, and it can now begin communicating out on the network. So we have this process of discover, offer, request, acknowledgement, and we can remember that very simply with the acronym DORA, D-O-R-A. And that's going to allow the client to start communicating on the network and receive that DHCP assigned address, a DHCP initialization. I've switched over to Wireshark now, and I've opened up a file called DHCP NoLease Initialization.pcapng, and this packet capture is going to show you exactly what we just talked about, that 4-step DORA process. As a matter of fact, you can actually look over here at the info column and spot that pretty quickly because it's going to show us the application layer metadata. It's abstracted with the protocol dissector, so we see DHCP discover, offer, request, act, all in here nice and tightly together. So we know this is that DORA process, and I'll show you another thing of interest is we actually know that this is all part of the same DORA process because look over here. We have a transaction ID value, and they're all the same. We haven't talked about transaction ID, but it's this transaction ID value that allows us as analysts and also the sender and receiver to associate these specific requests together. So we know these are all part of the same transaction. If we had multiple DHCP requests going on in this capture, we would be able to track them with differing transaction IDs. Of course, if I go down here to Bootstrap Protocol and expand that, we'll be able to see those transaction IDs in the packet. Now, with that said, you may have heard me say bootstrap protocol, and this is one of those interesting artifacts in Wireshark, such that instead of just saying DHCP, the application layer protocol here says bootstrap protocol, not DHCP. That tripped some folks up. Obviously, I said bootstrap protocol was essentially replaced by DHCP as being more what people use now, but there are a few artifacts of that in Wireshark, and it's been that way for quite some time. So when we see bootstrap protocol here, we're actually referring to DHCP. Now, that distinction is important to note for one specific reason. Let's say I wanted to filter out all the DHCP packets in this capture. Well, I could go up here to my handy filter bar and type the protocol name. After all, that's how we normally filter things, right? Like if I type in HTTP, we're going to get all the HTTP packets. In this case, there are none, so we're not going to see any. Let's do that with DHCP. How about that? I didn't get anything back. The reason is because if you want to filter DHCP packets in Wireshark, you actually have to type in bootp, and then you'll get those bootp or DHCP packets. Not the most intuitive thing, I don't think, but once you mess it up and bang your head against the wall for about 5 minutes the first time, you'll learn that lesson and never do it again. So that's the important thing. You just use bootp as your filter if you want to filter only on these DHCP packets. Now, with that out of the way, let's go ahead and dig into the meat of this DHCP packet. And I want to call out one thing specifically first. Notice that DHCP relies upon UDP. It's not a TCP-based protocol. We're using UDP here for this communication. So take note of that. That's important. You also see we're utilizing ports 68 and 67, which are traditionally assigned to DHCP. So that's another way you can filter based upon this is via those two specific ports. Now, if we get down here into the DHCP section, we have a lot of different stuff going on. There's quite a few fields. Only a few of them are particularly relevant to us, so we're going to focus on those. First of all, we have the message type field, and it says boot request. Now, this is message type, but it's not message type in the sense that we talked about earlier, where we have discoveries and offers and request and act. No, it's a little bit different. For here, there are only actually two message types available, and they're actually used to define whether the DHCP packet is a request or a reply. So if you'll notice in this initial packet, we have boot request, which value of 1. If I click into the second packet, we see boot reply, which is 2. We see the same thing in the third and fourth packet. We see a boot request and a boot reply. So basically that's just telling us whether it's a request or reply in relation to the DHCP client. That's specifically what we're looking at there. The next thing of interest is this hardware type field, and it says Ethernet. And what that's basically just telling us is that this communication is going over an Ethernet network, and as such, the address length we're dealing with is 6. So that's important to know that we're going over an Ethernet network, since we're communicating without the benefit of IP addresses initially, right? We're broadcasting to the broadcast address to find our DHCP server without actually having a valid IP address. So that's useful information. Now, there are a few other things in here. I'm not going to go in depth on all of these. You can certainly read about more of those in the RFC. We have a lot of IP addresses here. So you see something like client IP address, your IP address, next server IP address. And the thing of note is we don't actually have any of this information right now, right? We don't have an IP address. We're not using DHCP relay. We don't really know anything about anything right now. So that's why these are all zeros. In one sense, this is kind of why DHCP as it exists in this form is a bit of a bloated protocol. We're having to waste space on all these zeros. When we look at DHCP v6 later, you'll see how it's a little bit more efficient. But for the purpose of DHCP, it's not the most efficient protocol in terms of having excess fields that aren't always used. Not a big concern, since DHCP isn't a really high volume protocol in many networks, but notable in this case. Now, next we have the client MAC address. You'll see that here, that if we scroll up, that's going to match the MAC address we see here in the Ethernet header. So we see that value. We're including that because that's how we're communicating at this point. And then from there, we get into the meat of this, which is actually going to exist in the options section. And I know that's a little odd that the meat of the communication, the important stuff, is going to exist in the options. We think of that normally in the main protocol header, but nonetheless, the way DHCP is structured is most of the main stuff that we're concerned about exist in the options here. And we see quite a few of those available. The first one we'll look at is the DHCP message type here. option 53, and I'll expand that, and we see we have a length of 1 for the field, and in this case it is DHCP discover, and that's consistent with what we see up here in the info column, that this is the first step of that DORA process. It is a DHCP discover packet, and we kind of glossed over this a minute ago, but if we go back up to the UDP, the IP section here, we see that the source is all zeros because we don't have an IP address yet, and the destination is 255, 255, 255, 255, which is the network broadcast address, meaning that this packet will be broadcast out as a DHCP discover to every device on the broadcast domain. So we better hope our DHCP server is in that broadcast domain if we want to receive it. So that's consistent with what we would expect. Normal stimulus and response, you'd expect the DHCP discover to be sent out in a similar manner, at least for a normal DHCP initialization process. Now we have a couple of other useful pieces of information down here in the options as well. One of those is the requested IP address, and in this case you see we actually have one here, 192.168.100.129, and there's a number of reasons you might have a value here. In some cases this could just be all zeros, meaning no requests, specifically requested address, or it could be just a previously used IP address. Now this doesn't mean the DHCP server has to honor this request, and I think you'll see here in a moment that ours actually doesn't, because we're on a different network. We have a device that's changed networks. But if there is a previously used address, the client will try to potentially reclaim that by requesting the IP address here in an option. We have the hostname value here, which shows the hostname Ubuntu 2, which is this hostname in this case. We also have, more importantly, I think, the parameter request list. And these are all the different things that the client is requesting if they are available. And some of these are things we talked about, right? Subnet mask, network broadcast address, the router, so we're talking about the default gateway here, as well as DNS related information, and we have a few other things as well. We see a host name, NetBIOS information, and so on. There's a lot of things that can be included in this, and what gets sent back is based upon how the DHCP server on the network is configured and what information is pertinent to that network. But the client can request all these things. The server doesn't have to reply with really any of them, but this is what the client's saying that it will is requesting and will accept in this case. So that makes up really the bulk of this DHCP discover packet, or at least the parts that we're concerned about. There's not a lot of useful information here because that system doesn't have a lot of useful network information. It's basically sending this broadcast out on the broadcast domain of the network to say, hey, any DHCP server that's out there, please respond and provide me with addressing information so I can begin to communicate with other people on the network or even outside of the network to other hosts. The next packet on our sequence is the offer packet. So our client has sent out this broadcast and someone thankfully has replied. And in this case, we see the reply is actually from, we can see in the source and destination field, the source is 192.168.1.5. That's the IP address of our DHCP server. And it's actually sending this directly back to, in this case, 192.168.1.10, which is actually the IP address that it's offering to the client. Now this doesn't mean the process is completed yet, but nonetheless the appropriate information is now included if we scroll up here in the IP header. So that information is there, whether that's actually being used for communication or not. In this case it's just a simple reply to this broadcast, and the device hasn't fully accepted these configuration parameters quite yet. Now, if we go down to the Bootstrap Protocol or DHCP section here, first of all, we see that it's a reply. We've talked about that. This field just indicates whether it's a request or reply in relation to the client. This is a reply to the client. And then we actually see some information populated in some of these fields that were all zeros before. First of all, we see the your client IP address. This is 192.168.1.10, and this is the IP address that's being offered to the DHCP client to accept. We also have the next server IP address field, and this is actually the IP address of the DHCP server, consistent with what we see above in the packet list window with the source and destination information. So we have that information there, and that's really a lot of the things we need. Now, we also have a few interesting options here to look at as well. These are different things provided by the DHCP server, some configuration information and additional addressing information. One, we see that this is a DHCP offer, so that's consistent with what we see above. That's type 2. We see a DHCP server identifier, which is identifying it by an IP address here. And then the next thing, which is of interest, is the IP address lease time. So the DHCP server not only is responsible for handing out IP address and information, but it's responsible for determining what the duration of that lease is. So when we say a lease, we're saying that that system, that physical system, it doesn't own that IP address. It's just allowed to use it for a set amount of time. And that amount of time is configurable. In this case, the IP address lease time is 10 minutes. So that IP address is only valid for that period of time. Now, we have a couple other pieces of information offered. For instance, we have a subnet mask here. We have a broadcast address for the network. We have the router, the default gateway for the network. We have the domain name, and we even have some DNS servers. So this is all information being provided for the configuration of the client that it can then choose to accept, which is what will happen in the next step. Now that the information we need is provided, the rest of the process is pretty simple and almost to some degree a little bit of a formality. We'll look at the request packet here. In this case, we go to the options. We'll see DHCP message type is request. That's type 3 in this case. We have some proper information now filled out for DHCP server identifier. So it's actually clearly identifying our DHCP server in this case. We have a requested IP address, and now it's the proper address. It's the actual one we're supposed to be getting, so we're formally requesting that one. And then we see the same list of requested parameters that we saw before. Granted, we're not going to get all these things, but it is the same list that we saw in the Discover packet. Finally, the server is going to acknowledge this, and this is going to be if we look at the options here, message type ACK, which is actually type 5. So that confuses people. We went 1, 2, 3, 5. So we actually skipped 4. That's not the next step in this process and a healthy initialization. But we do, at this point, we're wrapping up. We have DHCP server identifier, again, the same address. The lease time, it's really all the same information we just saw that's repeated again in this fourth packet. Maybe not the most efficient thing, but it's what's working for us here. So that's going to show us the entirety of this DORA process. From a general troubleshooting perspective, you may not always need to actually get into this level of detail, going into these options and looking at things. A lot of the pertinent information is displayed here in the info column, as Wireshark's good about doing, the message type in the transaction ID. But if you need to dig in and see what addresses are being offered, what's being identified, where problems are going on, then you might want to do that down here. When we talk about abnormal stimulus and response in here in just a minute, we talk about rogue DHCP servers, identifying the MAC addresses for these specific servers to find out maybe what they are, where they exist, is also a useful technique. But nonetheless, this is the DHCP initialization process for a host that is outside of its lease, and this will allow a network device, once plugged in, to retrieve an address from a DHCP server, and is really the basic, most fundamental level of DHCP communication. Now, I want to show you one more type of stimulus and response that's expected and normal for DHCP renewal, but this time we're talking about a host that is within its lease, so a host that already had an existing lease. And remember, when we looked at the packets, we saw that a DHCP server doesn't permanently assign an IP address to a host. It gives it a temporary right to use that IP address and information, and then maintains a log or a table of that information within its own internal database. Now, those leases are time limited. We saw in the previous example, we had a 10-minute limit. So what happens when that lease is over? What does the system do? Well, generally, it's going to get the same IP address back, but it's only because it's requesting it. And it's going to request that through an abridged version of the renewal. So there's no point of going through that whole process. Remember, the whole initial process was because we didn't know where our DHCP server was. We didn't know anything about the network. We didn't know its addressing scheme. We just didn't know the darndest dang thing about that network. So now that we actually know a few things about it, we can actually abridge that process a little bit. So whereas before we had a client and a server and went through that whole discover, offer, request, ACK, the process for an in-lease renewal is actually half the process. It's only the request and the ACK. We don't see the discover, we don't see the offer because the DHCP client is much more aware of the information it needs. So this is the process you would expect to see, is just the request and the acknowledgement, not the discover and the offer. And that's normal stimulus and response. I've seen some people who will be looking at DHCP traffic and they'll say, hey, something seems wrong here. I mean, I'm getting an address, but I don't see the discover and the offer. And that's because it's just a renewal for a host that was in lease, which is going to be a little bit different, but really just half of the DORA process that we looked at a minute ago. I'm only going to talk about one type of abnormal stimulus and response for DHCP servers here because I think this is really the most common thing you might see. And it's not even entirely common in terms of malicious activity, but more just misconfigurations. So let's imagine a scenario where we have a DHCP client. We have a device we plugged in the network. We want it to get IP address and information so it can communicate over the network. Well, what's it going to do? It's going to do what we talked about. It's going to send a DHCP discover packet out across the network. And the idea is that the appropriate DHCP server within its broadcast domain, this little blue guy up here on the top right, will respond with an offer packet. But let's consider another option, another reality. What if that's not the only DHCP server on the network? What if we've got this orange guy down here at the bottom, this rogue DHCP server? Now, when we say rogue, that could be one that's operated by a bad guy, or it could be one that's just misconfigured, one that's not supposed to be there. But nonetheless, what happens when that broadcast packet goes out and there are two DHCP servers within that network range? Well, they're actually both going to respond. They're both going to send an offer to that DHCP client. And you would ask, well, which one's it going to respond to? Is it going to respond to both? And generally, no, it's going to respond to the first one it receives. So it's essentially a race condition. Whichever device can respond faster and whichever response the client gets faster is the one it's going to complete the process with. So it's going to send the request to whichever of those systems it is. So that's a race condition in that whoever gets there first wins. Now, that can cause a problem. Generally speaking, within the same network segment, from a network architecture standpoint, you should never really have two DHCP servers on that segment because you only want one DHCP server handling that responsibility of passing network information out. Now, you could say that maybe there's some type of load balancing you're doing and you're getting creative there, and I suppose that's the reason you might do it, or there are a few edge cases. But for the most part, you don't want two DHCP servers handing out the same range of addresses on the same network. Otherwise, you're going to end up with different devices that have the same address. And anytime two devices on the network have the same IP address, you're going to have a bad day. You're going to have all kinds of weird problems that are hard to explain, and you're going to pound your head against the wall for a little while. So that's not a good deal. Now, there are a lot of reasons something like this might happen. Like I said, the most common is misconfiguration. I've seen many people who will go buy a wireless access point off the shelf, plug it into their network to extend wireless coverage, and not realize that that access point has a DHCP server running by default. And what you've done at that point is introduce a rogue DHCP server to your network, which will create this very problem. The other option here is that an attacker might do this. An attacker who has maybe physical access to your network or maybe just software access and they want to set up a DHCP server. If they do that, they can actually trick your clients into communicating on a completely different network by handing them different IP address and information. This could create a denial of service condition. It could create a condition in which confidentiality is being breached or which integrity is being damaged in a non-positive way. So it is a thing where it could be a bad guy doing something you don't want beyond just a misconfiguration. All that said, virtually every time I've ever seen this has been the results of a misconfiguration. Like I said, somebody plugging a wireless access point or something into a network that already has a DHCP server running. So the tricky thing about this is the only real way to detect it, unless you have specialized software to do it, is to look at the packets, is to, if you have a host and it's getting an IP address you don't expect, or it's having trouble getting an IP address or something like that, if you capture the packets and see that you have two devices responding to your discover, you're getting two offers, because you'll see the second offer. The client's not going to respond to it, but you'll see both offers come back. So that would be the thing that would be weird, is if you send a discover and you have more than one offer coming back. And then, of course, you can see which one the DHCP client is continuing the conversation with based upon which one got that first. But nonetheless, this is the abnormal stimulus and response that occurs when a rogue DHCP server, or at least a second or third DHCP server, winds up on the same broadcast domain as another DHCP server.